Is it working? Oh, it looks like it. Okay. Hey, everybody. Okay. Oh, well, that, oops. Looks like it was playing in the background there. Okay, so now that we got that all straightened out, let's start with the $10 questions before we get into before we open it up to everybody else. It's standard procedure if you haven't been to one of these yet, but we got a few of those to go through, and I like it because it kind of sets the stage for the rest of the hangout. So here we go. All right, there should be a chat box open. Yep. Okay, good. So let's see here. All right, so we're going to start with the first question here, which is, let's see, David Kumarbai, I think. I'm bad with names. Anyway, so what planet would you colonize first if you had access to all currently accessible resources on Earth and the current manpower, including brain power and just raw strength, to utilize those resources? Well, I think it would have to go Mars. I know that's kind of cliche, but Mars has been just it's excited the imagination of human beings for a very long time, and I think it'd be a lot easier to get other people excited about colonization of another planet if it's Mars. And I realize there are some arguments in favor of Venus, but a Venus colony would have to be a cloud city, and I would prefer that the colony that I'm building be on the ground, just for safety reasons. So there's that. But both are kind of viable options. But I would definitely pick Mars over Venus. I think Mars is just cool, All right, so let's see what else we got here. LS Greger has a question about LIGO. Says they consist of two lasers in a vacuum about 4 kilometers in length. How did they come to that length? Would it ever be possible to create gravitational wave detectors on a much smaller scale, or does the nature of those waves make that impossible? Okay, so a few things about LIGO. First of all, yes, the two arms of LIGO are 4 kilometers long, and there's a few reasons there. One, I mean, the longer you build them, the more expensive it's going to get, and so there's a limit. Now, why they came up with the 4 kilometer limit, which, by the way, 4 kilometers is about 2.5 miles, in case anyone needs it in miles. The reason for that is after about 3 miles or so, you start to have to really worry about the curvature of the Earth and how that's going to affect how straight you can make the arms of this detector. And so 2.5 miles is a pretty decent measure of, keeping it within the realm of approximately flat Earth surface, right? So you can, over that distance, you can more easily make the ground as flat as possible and therefore make the arms of your detector as flat as possible. However, an interesting thing about LIGO that doesn't actually get talked about very much is that even though the arm of the detector is 4 kilometers, the actual laser isn't. Right? If it was only 4 kilometers, it actually wouldn't be big enough to detect the gravitational waves, right? We need to detect the fraction of the diameter of a proton, which is very tiny, right? And so we need a very long laser, a very long distance for the laser to travel. And so what they do is they actually set up a couple mirrors at the two ends, and the laser actually bounces back and forth like over and over and over again before it actually gets recombined with the laser from the other arm. And so even though the arm is 4 kilometers, the actual distance the laser travels is, let me see here, I wrote this down, 1,120 kilometers. So quite a bit further than the 4 kilometers. And so what that does is it basically makes the LIGO detector about 144,000 times bigger than the original interferometer that was built back in the 1800s, the Michelson-Morley experiment that was attempting to measure the speed of light. But it's called an interferometer, and that thing was built a long time ago. But this is so much larger, and it has to be. You can't really make a gravitational wave detector that's the size of, that's like a meter long or a yard long in either direction. So it's just too small. Okay. Next question. Let's see here. It's a great username, Skibbity Boo. Reminds me of scat music. But if you surround a spinning black hole with mirrors, then fire electromagnetic radiation into its ergosphere. Without a way for it to escape, will it explode? Asking for a friend, says. Probably. I know Kurzgesagt did a video about this a while back. In fact, I linked to it in the description of my recent rotating black holes video. But they sort of go into it a little bit now, and they talk about it. What do they call it? Super radiant scattering. And so yes, this would occur inside of a mirror ball that was surrounding a black hole, but it wouldn't exactly look the way that Kurzgesagt drew it. And obviously they have animation limitations and stuff, but the paths for light around a black hole don't exactly look like you'd expect the path for light to look like, straight, right? Straight lines look a little different in curved spacetime. And so while that scattering off the mirrors does occur, it doesn't really occur in straight lines like you'd expect it to occur in a spherical mirror without a black hole in the middle, right? So things look a little different, but it would, the light would gain energy, right? So if you put the light in there and you bounced it off the mirrors, it would gain energy as it passed through the ergosphere, as long as part of it entered the black hole. So something I mentioned in my video was it was called the Penrose process, proposed by Roger Penrose, which is why it's named after him. But the Penrose process, it involves part of something getting away from the black hole while another part falls in, and that part falling in is very important for the process to work. And so the light would pick up energy from the rotating black hole. It would sap away rotational energy from it, as long as part of the beam fell into the black hole and made the black hole's event horizon grow, right? So one of the requirements of this is that the black hole's event horizon grows. It must increase in surface area, no matter what. And it just so happens that some circumstances you can increase the surface area of the black hole while also making it slow down in its rotation. So as long as the event horizon grows, then you can sap energy away from the black hole, no problem. So some of the light actually has to fall in, it has to cross the event horizon. But the light that remains outside will zip right back out of the ergosphere because it's traveling at the speed of light. And it would, and so it would go out and reflect and keep reflecting. And so as long as all the light didn't fall in, right, as long as there was always some light on the outside to sap the energy away, it could explode. It could. It doesn't necessarily mean it will. Depends on how much energy the black hole has to give in terms of rotation. But it could, yes, and it would be a very, very large explosion if it did. So, sort of a long-winded explanation, but I want it to be as accurate as possible. All right, so next up, we got JKLMN Anderson, which told me is Mark Anderson, which I think the username is interesting. But says, what corrections are done to observe galaxy light in terms of redshift? Is there a gravitational redshift from the galaxy itself? Yes, there is, and that's sort of the problem with redshift. And so when we're trying to measure the redshift of a galaxy in order to measure what we call cosmological redshift, that is, in order to measure the expansion of space over time, we can't do that on every single galaxy. It just doesn't work. There's a lot of other factors that come into play, like gravitational redshift, because the gravity of the galaxy will redshift the light that is zipping away from it. You also have other types of motion, like Doppler redshift has to do with the motion of the galaxy itself relative to you, and so those all redshift the light, and there's really no way to tell from the redshift value how much of it is redshifted due to each effect, right? Cosmological, gravitational, or Doppler. And so if you want to be sure that you're measuring cosmological redshift, you have to go way, way out, right? You have to go not outside our local group, right? And further than our cluster, the Virgo cluster, you have to go all the way outside of our supercluster of galaxies before you can be sure that gravitational and Doppler redshift are small enough to ignore. And so when we map out the redshift of distant galaxies to try and get an idea of how fast space is expanding, we have sort of a blind zone in the local area, right, in our local supercluster, where we can't really be sure what's what. But outside of that, outside of our supercluster, we have a very good handle on the fact that these galaxies are moving further and further away. Okay, so the follow-up question there was, any comment on the alternative method of measuring the expansion of the universe and that not agreeing with the redshift? Well, okay, so right, there are two ways that we can actually measure the expansion of the universe. Well, the expansion of space. Space and the universe have slightly different meanings. So space is expanding over time, and we can do that by measuring the redshift of galaxies using things like standard candles, things that we know what the light should look like so that we can compare it to what the light actually looks like and measure a redshift. And so we can use those standard candles to measure the redshift of galaxies. The other method is through little tiny variations in the cosmic microwave background, or CMB, which is a very big deal in cosmology. It contains a lot of information for us. So there's ways that we can figure out things about that and then sort of extrapolate forward and figure out what the expansion rate is now. And using those two methods, the redshift of galaxies and the CMB, the numbers are very, very close, but the error ranges are too small, and the ranges don't overlap with each other, and so there appears to be some kind of discrepancy. I'm not sure where the problem is, and I mean, obviously, cosmologists aren't even sure where the problem is. We're still trying to figure it out, but What that shows us is that there is some minor detail in something in one of the methods that we're either doing wrong or we're not understanding quite right or whatever. And there's a lot of steps that go into that, right? So either we don't understand the standard candles like we think we do, at which point the redshift data will be slightly off, or uh, we don't understand how dark matter and dark energy work, which would make the CMB data be a little off. I should say the CMB calculations. And so it could go one way or the other. We're trying to figure it out. We're ruling out things, one at a time, but there are still a few things we haven't quite figured out there. But yes, there is a minor disagreement between the two methods, and it's something we definitely have to resolve. But the nice thing is it could lead to whole new types of physics. So that would be really awesome, actually. Discrepancies like this are a really, really exciting time. It doesn't seem like it should be, but it is. Speaking of the CMB, Vittorio wanted to know if we could consider the CMB to be an absolute zero for time. And that would be a hard no. As far as zero goes for time, we can really put zero wherever we want. That's sort of the nice things about time, and it's sort of invariance, right? But if we want to treat an absolute zero for time, like the very beginning of time, that happened way before the CMB was released. And so the CMB is certainly 13.8 billion years old, just like the universe is, but it was released hundreds of thousands of years after the beginning of the universe, right? And 100,000 years or 400,000 years is not that big of a deal when you're talking billions. And so even though the universe and the CMB are roughly the same age, they're not exactly the same age, right? In terms of a human lifespan, there's a lot of time in between the CMB release and the the beginning of the universe. And so a lot of stuff happened in between those two moments. And so I would say definitely not. The CMB is definitely the furthest back that we can actually see with light, because it's the first time that light was free to move through the universe and travel for 13 billion light years. Before that, it really didn't get very far. And so it's definitely the furthest back we can see with telescopes and devices and stuff, but it's not the beginning of the universe. So hopefully that clears some things up. Okay, so that is it for the $10 questions. We're gonna open it up to the chat. I've got the chat open here, and I've been kind of watching it as I sort of answer these questions. So let's zip up to the top here for a minute. Got some follow-up questions here. So as far as colonizing a planet, Maxim said maybe one of Saturn or Jupiter's moons is more suitable for humanity. Maybe Saturn's Titan or something, but the further out you get, the colder it is, and the more you have to rely on our own technology to keep things warm and stuff, and that can get kind of dangerous. And so I think while one of Jupiter's moons or Saturn's moons would be a good place to go after Mars, I think we should try something easier first to sort of just get our feet wet a little bit and get a feel for some of the obstacles we might run into before we start venturing out further. Mars colony would become mole people. I mean, it all depends on how long you give it, right? I mean, if we send humans to another planet, we could very easily, evolve into, Earth humans and Mars humans could very easily evolve into different species that can happen. It's happened throughout Earth's history quite a bit when groups of a single species get separated, right? Just depends on how much time we give it. Let's see. As far as LIGO goes, it says, how about 1.5 million kilometers apart? There is a project to use such distances in space. Sure, I mean, you could do that. You could put that in space, but the problem is you need to make sure that I mean, you can't build something 1.5 million kilometers long. And so the central hub and the two mirrors at the end of the arms would have to be three separate satellites, and then you'd have to make sure that they remained aligned with each other. And there's a lot more work that goes into making a space array than it does to make one on the ground. And so I like the fact that we made two just to start, so we could get some idea of direction, and then other countries are now building their own detectors so that we can compare notes, and we can get a much finer measurement of where some of these gravitational waves are coming from. But so yes, a space array would be cool, but there are a lot more obstacles involved in building one of those. With regard to the Michelson-Morley experiment, says they were looking for the ether, right? So the luminous ether, that doesn't really contradict what I was just saying. What the interferometer, the light interferometer, does that Michelson-Morley used back in the 1800s was it was designed to measure the speed of light. Now, if there was a luminous ether, a substance through which light moved, then Earth should be moving through that substance, at which point the light beam should be traveling a different speed along one arm than it will be along the other. And so the idea was, if you could measure the speed of light in two different directions and then make sure you rotate your interferometer and take measurements from all sorts of different directions, then what you can do is then you can sort of, based on the speed of light data, you can figure out what direction the Earth is traveling through the ether and that sort of thing. But when they did the experiment, they found that the speed of light was the same in every direction. And so there were only a few possibilities. Either the luminous ether doesn't exist, which is sort of the conclusion we came to now, or, for example, the Earth carries a bubble of luminous ether with it as it moves through space, which would fix the problem, but is kind of ridiculous. And the third option was something that was proposed by Hendrik Lorentz, which was that the luminous ether contracts or expands the interferometer, the measuring device, so that it conspires to keep the speed of light the same, which kind of turned out to be right, but for a completely different reason. It turned out to be length contraction, which Einstein eventually used in his special theory of relativity. But so that did turn out to be the case, but for reasons that were completely unrelated to the luminous ether. And so at this point, we are pretty sure it doesn't exist. But the point is that the interferometer measures the speed of light, and from that we can infer the speed of the Earth through the ether, or vice versa. And so that is kind of related historically. Hello from down under. That's wow. This is late for you, right? I mean, Australia is what, like 15, 16 hours ahead of me. It's the middle of the night for you. Wow. Thanks for coming, I guess. Thanks for coming to the live stream. Let's see. Hey, nice to see you again. Let's see some questions. Let's get away from these early questions here. Um, I read a couple days ago about Earth's atmosphere stretching far beyond the moon. Any comments on that? Okay, so that isn't really, the atmosphere doesn't just like stop at a certain point. We like to think that it just stops, but that's not really how it works. As we go up towards space, right? The density of air decreases, and it decreases pretty fast. I think about something like, is it like half the actual air molecules in the atmosphere are below the peak of Mount Everest, which is part of the reason that you need uh, you need a oxygen mask usually to be up there. But the point is that it just kind of trickles off and trickles off and trickles off, and it never really goes to zero. It just gradually becomes the density of empty solar system space, right? So if you want to get super technical, all of the planets in the solar system kind of have one atmosphere. It's just that it's really thin most places. And so there really isn't a boundary for space. Now, there are arguments as far as like, how do you define what space and what isn't, which is actually important for whether how you classify what an aircraft is and what jurisdiction, who has jurisdiction over regulating what the space, what the aircraft does, right? So there needs to be a clear definition between what a spacecraft is and what an aircraft is. And so they have to define a boundary between the atmosphere and space. But it's not a physical boundary. It's just one that we made up so that we can have some definitions and some laws and things like that. But technically, yes, the atmosphere stretches out to infinity, and it changes composition and stuff. But and very quickly changes density. But the point is, it's always there. Even GPS satellites, which are way out there, have a little bit of drag on them, right? So there are lots of satellites in space that have atmospheric drag, even though they're outside what we define as the atmosphere. So I wouldn't listen to an article like that if it's hyping up something. That's something we've known for a while. Uh, how do you think graphene will change the world, if any? I think, I mean, there's really no way to tell at this point. I mean, we have graphene, which is basically just a certain molecular structure of carbon, right? So we already use it in rechargeable batteries and stuff, but I'm sure it's going to have all sorts of other uses. Maybe filters or something. I mean, I couldn't. I don't know if I could speculate. I'm sure there are lots of uses that we'll discover over the course of the next decade or two, as we figure out how to produce it better. Um, yeah, it's nice that people don't burn other people at the stake for heresy over different calculations. I agree. I like that we live in the 21st century. It's a good time. Let's see. Was gravity a force at the birth of the universe? Technically, so in the very early universe, they always talk about how the four fundamental forces sort of gradually decoupled from each other. Um, it's it's kind of difficult to explain what that means exactly, but basically, uh, while we have four very distinct fundamental forces now, we've got electromagnetism, gravity, weak nuclear force, and strong nuclear force. In the early universe, those forces were very indistinguishable. And because of particle accelerator experiments, we've been able to figure out what conditions are required to make them indistinguishable, to get them to a point where we can't really tell the difference. And so we've done that with electromagnetism and weak force. That was done pretty early. I think it was like the 70s, the 1970s. Steven Weinberg. But we call it the electroweak model, right? Which is basically electromagnetism and weak nuclear force are indistinguishable at a particular level of energy in the system. And then we have some idea of where the strong force combines with those. That's something we call a grand unified theory. If we were to combine the strong, the weak, and the electromagnetism, we feel like we have some idea of where that should happen. But as far as gravity goes, we're not sure exactly. We don't really have our model for gravity doesn't really behave very well with the model for the other three forces, which is quantum mechanics. And so we have a hard time figuring out exactly where that's going to happen and if it's going to happen at all. We assume it would, but we don't actually know for sure. And so it's possible that gravity was its own standalone force at the beginning of the universe, at the beginning of what we would call time. But it might not. It might have been a combination with the other four. There might have just been one force, what we call a theory of everything. And so it just depends on what the next step in physics tells us. Let's see here. If a neutron star was on the verge of becoming a black hole, do you imagine the event horizon would be instantaneous across the entire sphere, or would it be gradual? Based on what I know of general relativity, I would have to say that it would be instantaneous. You would be able to see the surface of the neutron star, and then all of a sudden you wouldn't be able to see it. It's just kind of how it goes. And so now that's if you're a close-up observer. If you're a very, very distant observer, then things get a little weird. There might be a situation where you wouldn't necessarily see the last bits of neutron star actually cross the horizon because of time dilation, and so things get a little strange, and it could look a little unexpected based on where the light comes from and where it ends up. So there's some weird stuff you have to worry about, but I would say that on the whole, it is instantaneous. It's at one moment it's not there, and then the next moment it's there. Although it does kind of the place, right, of the event horizon, the place that we expect it to be, does kind of grow out from the center as the star collapses, and so it's less like an appearance of the event horizon and more like an emergence of it, right? So it's something that kind of like emerges from the surface of the neutron star as the neutron star collapses. And so that might help if you're having issues with anything happening instantly. It's kind of already there. Everything kind of technically has an event horizon somewhere, and it just becomes what we call an event horizon under certain conditions. Let's see. How do you tell the difference between a black hole and a neutron star? Well, it comes down to the mass that is collected in there, right? So if we if we see something that has a certain amount that isn't a star, right? That's a dead star, a star that is no longer fusing matter. So white dwarf, black hole, white dwarf, neutron star, black hole are our three major options. If we are looking at a particular part in space, a particular region of space, and we see an object that has a certain mass, like it has 5 solar masses, then there's really no way it can be a neutron star because neutrons can't hold up under that kind of gravitational pressure, that kind of gravitational collapse. Gravity will overpower the neutron pressure pushing outward and collapse it into a black hole. Period. End of discussion. Right. So, if we're talking around the boundary, the place where we transition from neutron stars to black holes, then there's some vagueness there, right? So if we're talking, say, 3 solar masses, which is roughly what we consider to be the upper limit for a neutron star's mass, then we might not be sure at that point, right? Because we don't know exactly where the boundary is, right? So it might be 2.9 solar masses, or it might be 3.1 solar masses, or 3.2, or something like that. And so, um, depending on what the mass is, so if the mass is close to that boundary, it's kind of in the gray area. But if it is well above 3 solar masses, then we are sure it's a black hole, and there's no ambiguity at all. Whereas if it's well under the 3 solar masses, like say 2 solar masses, then we can be very sure that it's a neutron star. All right, let's see. What do you think of NASA's new plan for the moon? I haven't heard any new plans for the moon. I know China just sent up a moon orbiter, which has sent back some really awesome pictures, by the way. But I haven't heard anything about NASA's plan for the moon. I know they're having, like, budget cut issues and stuff, but I can look into it. I didn't know that there were plans. So a moon base, because that would be awesome, but I'd probably not. Let's see. Um, let's see here. How many problems create error in physics calculations? I assume you mean error. Right. I mean, it depends on the circumstances, right? There's a lot of room for error. Like we were just talking about black holes and versus neutron stars and the borders, right? So we can be fairly confident that it's around 3 solar masses, but depending on exactly how neutrons behave in that really compressed state, uh, we can't really be sure exactly when they break down. Um, it's a much more difficult calculation to make. There are a lot of factors involved. We know that it should break down, and we have a rough idea of where, but because of the errors and the potential wiggle room in our calculations, at that point, I don't know if I'd call them errors. It's more just sort of uncertainty in measurements and stuff like that. So, we would need better measurements about neutrons in order to actually make any more specific claims. Um, okay. Hello from North Dakota. Yes, it's cold. I bet it's cold there. That jet stream is being real nuts lately, which is not the first time. We've been having some oddly warm weather here in Michigan, but let's see. What's the problem with using infinity in calculations? Well, I mean, there's no problem with using infinity in calculations. It's a really nice shortcut, and you can get a lot simpler results if you assume infinity and plug it in rather than plugging in, say, 10 billion. You can just plug in infinity and get a much better number. But the problem comes when you try to take that and relate it to the real actual universe, right? So you have to decide whether or not anything that we could possibly measure in the universe is infinite. And I would distinctly say it isn't. Whether the entirety of all space is infinite is not really the issue here. What all we can really observe is the observable universe, which is definitely finite, but it is very, very large, right? And so if you want to say that an electric field stretches out to infinity, you would say infinity. You wouldn't necessarily say the end of the universe and then plug in 3.8 billion light years. It's much easier just to say it stretches out forever, because as far as we're concerned, 13.8 billion light years away is an unreachable place. And so that's infinity. But what I'm saying is that, like, you have to be careful about how you attach the word infinity to the real universe, because the real universe, the part that we can observe anyway, doesn't have anything infinite inside it ever. And so it's a nice tool, but it doesn't actually exist. How do we calculate the half-life of pretty stable elements, those with billions of years? Well, I'm sure a lot of it is experimental. We have ways of measuring, the rate of decay over a short time period, and then we can kind of extrapolate based on that portion of, a graph that we might draw, that, the half-life is a certain time away. But some of it is based on predictions that we make, right? So it's not necessarily about experimental measurements. It's about what we know about that substance, like uranium 238, for example, is the reason that we know how old the Earth is. And so we have these very old rocks, and we can uranium date them. It's kind of like carbon dating, but way, way bigger timescales. And so we can uranium date them back to 4.6 billion years ago, based on what we expect uranium to do over time, right? Based on how many neutrons it has and how many protons it has, and what we know about how those particles interact with each other. And so our predictions about those elements seem to be consistent with the measurements we take of them over short time periods. And so we can be fairly confident that our understanding of them stretches to long time periods. But of course, there is some uncertainty when you extrapolate out like that without proper data. And so the further back in time we go, the longer the half-life of the element, the larger the error is, the larger the uncertainty is, and the measurement we're trying to take with it, the dating that we're trying to do. And so, while carbon dating, you can go back, tens of thousands of years, and only have like maybe a few hundred years of uncertainty in either direction. The uranium dating goes back billions of years and then has errors of millions of years, right? So there is much, much larger error in the larger timescales than there are in the smaller ones. So we have, it's one of those uncertainty things again, right? We have some idea, but not specific ideas. specific numbers to be able to calculate. Argument back here, there are many stars bigger than 3 solar masses that are not black holes. Yes, that is true. But if they're actual stars, then they're emitting actual light, and we can detect that light, which black holes don't do. And so, you take the mass in a particular region, and if we don't see the spectrum of a star coming from that region, then we know that there isn't a star there. And if there isn't a star there, then it has to be a black hole, like, process of elimination here. It has to be there. And I know there are some very, very serious people, a lot of people in the comments of my black hole videos that just show up to make a point to comment that black holes don't exist, which, if you're saying that, then you don't know how much data we have to support their existence. There's just an unimaginable amount. And so it's just, I mean, there's nothing else that it could be other than a black hole. It's the only possibility. And so while it is possible that there might be something called a quark star that could be in between the neutron star and the black hole, we kind of cram it in there for a little bit. We're not sure exactly where that sits and whether or not it even exists. But once we do figure it out, it would definitely have clear boundaries, just like the white dwarf does and the neutron star and the black hole, right? These are long dead stars are some of the things that we know the most about astrophysically. And so probably because they're the most fascinating, and so more people are studying them. But we know a lot about these, and so black holes definitely exist, and we can be very, very confident about an object being a black hole when we find one. Okay, so let's see what else we got here. Do you think that Mercury could be the remaining core of a hot Jupiter? Probably not. The thing is, we are getting our understanding of how solar systems form sort of called into question a little bit as we look out into space and we see other solar systems with these huge gas giants being really close to their stars, what we call hot Jupiters, right? So that seemed very strange to have happen, but the problem is that even with a solar system that could form a hot Jupiter really close to the star, there are a few issues, right? So one, it might have been a hot Jupiter might have been a planet that has been slowly, gradually drifting, spiraling into the star, where its orbit isn't quite as stable as our Jupiter's orbit is. And so it didn't actually form as a hot Jupiter. It formed as a cold Jupiter and gradually made its way in, sort of gobbling up the inner planets as it went. But even and so I think that's the general consensus as far as how these things happen, how these hot Jupiters happen. But even if they could form close, we're pretty sure that they have solid cores and stuff. But I don't see how a Jupiter-sized planet could have formed in our solar system and still had Venus and Earth have stable orbits. And so even if for whatever reason a hot Jupiter formed and that Mercury is what's left of one, I can't see that Venus and Earth would it even exist in the solar system if that was the case. And so just as a just to sort of handle the other side of that, right? If one did form in our solar system, it would have prevented the formation of Venus and Earth. And so I think the fact that Venus and Earth exist sort of negates the possibility that Mercury could have been a hot Jupiter. That's my professional opinion. Let's see here. So singularities aren't real in the way of infinitely small. Right. So this is something I actually mentioned in my rotating black hole video, as well as several other videos. When we get infinite results, like we look at the metric that describes space-time around a black hole, and we see a spot that goes to infinity, like an event horizon or a physical singularity or something, we have to be able to interpret what that means. And so when it comes to what we call a physical singularity, a point of infinite density, uh, we have to consider the fact that nothing else in our universe is infinite. And so we shouldn't expect something in a black hole to also be infinite. It kind of goes against our general knowledge of the universe. And so you can talk about them being in existence because we don't have anything that says otherwise yet. But I am confident that at some point, especially if we can combine general relativity with quantum mechanics, that we will learn that infinite density is not a thing. And so then a physical singularity is not a thing that exists. It's just a glitch in the math. Um, and so I don't think that they actually exist. We don't really have to worry about it because they're inside of event horizons and we can't see inside of event horizons. So people aren't really motivated to answer that question. But based on what I know of the rest of the universe and what I know of what has historically happened with singularities in other models of physics, I suspect that we'll find in a future model that they don't exist inside black holes either. We had a lot in electrodynamics with point charges like electrons for a while before we learned quantum mechanics and we learned that their positions and sizes were not exactly what we'd expect them to be. And so the actual point charge gets smeared out over space instead of just being a point. And so an electron does not have an infinite density, which is a topic I will definitely get to in a future video as soon as I can get back to quantum mechanics. But I am waiting on I'm waiting to hear about something kind of top secret. So before I can actually start that series, so it's going to be a bit, but I will get back to it and I will address the sizes of elementary particles a little bit better than I have in previous videos. See. I love the recent energy flow video. Shared them with lots of my friends. Thank you. Thank you for sharing. That video has been fairly controversial. I have a few very, very passionate people arguing with me in the comments, which is why I pinned that comment to the top of the comment feed, explaining a few things. But they're still there, and they're still arguing with me. I've started to ignore them because it's getting exhausting, and I just refer them to the pinned comment. But it's been controversial in at least educationally. Like I simplified things a bit, and people who understand the deep inner workings of how these vectors behave and are related to each other are getting all over my case about how I simplified it. And that's just that's something that happens when you're educating. It's just something that you're going to get people that are going to be unsatisfied, right? That I'm not complicated enough. And it just means I'm not for them. But and so in case you see them down there in the comments, that's all that is. Do not engage. They're just trying to, say their piece and move on. So, but I enjoyed making that video. I had a really good time with it, and I'm really happy with how it's performing and that other people are liking it. So, thank you for sharing. Would the switch from neutron star to black hole actually be a range of probability as you increase the mass of the star? Yeah, probably. Probably. Probably yes. I'm sure at some point, since quantum mechanics is necessary for understanding why the neutron star collapses in the first place, um, quantum mechanical uncertainty would definitely be involved in the value of the upper limit for the mass, right? Some neutron stars might form at a slightly lower mass, or some at a slightly higher mass, right? Depending on quantum uncertainty. Now, that uncertainty is going to be small, and so I don't know if it's going to be noticeable on an astronomical scale, but definitely will be there on some level. Let's see. Are these live streams stressful, or are they rewarding for you in a different way? Both, I think. Um, one of the nice things about producing video is that I can be very careful about the words that I choose to use and how I choose to say phrases and certain things and explain stuff. And I can't really do that in the live stream, right? You get to hear all my ums and uhs and my pauses for stop, for to think and that sort of thing. And so that's stressful, having me sit there and think. This, you kind of get pressure. I felt very pressured the first time I did one of these back in September. I'm a lot more comfortable now. If you haven't noticed that I'm stressed out, but it is kind of stressful in a way because I kind of take these questions on the fly, and then I have to very quickly think of a way to explain it that's going to make sense. And since it's on the fly, since I am not taking the time to think about my answers and run them by people before producing a video, I may run the risk of being slightly wrong occasionally. I try to be very careful about what I say, but it might happen. It might happen in the live stream that I say something slightly wrong and someone might eventually correct me or something. But so that can happen when I'm taking questions on the fly. But I think overall, I like being able to talk with you directly. I get to see your responses, right? I can say something, and then I immediately get a response, and and I can respond to it verbally, and it's actually really fun. It's very different than the comment section of the videos. I don't think I could do this publicly. Like, I don't think I could do a public live stream on the channel where, all 125,000 subscribers could show up and start asking me questions. I think I would get a little overwhelmed. But I like how personal this is because it's just supporters. Some of you are supporters on Patreon, and some of you are members of the channel over on YouTube. And so I like that it's smaller. It makes it more personal, and I can keep up with the chat feed a little better. So that's nice. It's only what it says 14 watching now, but some people come and go, and so it's a cool way to interact with you. I think I like it. While it is stressful, it is also rewarding in a different way. Let's see here. Why is Uranus so weird? I assume we mean, well, I mean, it's weird in a few ways, actually. one way, it has absolutely no cloud detail whatsoever, so it's sometimes considered the most boring planet. It's just this solid shade of teal, but it's also rotating on its side, which is a bit odd. Um, but it's not it's not something that we were surprised by. It just means that Uranus got hit by something heavy early in the solar system and it kind of knocked it over. So then now that it's spinning on its side, and because it's spinning on the side, it has some weird seasons. Like the poles can get a summer and a winter, and then the equator actually is more like the poles here, where it's generally just cold. And so um, things get a little funky, but it's not. I mean, it's unusual in the solar system, but I wouldn't be surprised if we ventured out into the galaxy and found other planets rotating on their sides. Uh, it's not so unusual that we wouldn't expect to see it. Can we make reliable mathematical model for a black hole without infinity? Not really. It's it's kind of the situation we end up in, right? So um, once the radiation pressure, the outward radiation pressure of the star is gone, it stops fusing and it collapses into whatever stellar corpse it's going to be. We have to invoke quantum mechanics in order to stop the collapse, right? Even with white dwarfs, it takes quantum mechanics. Neutron stars, it takes quantum mechanics. And so uh, if we want a model that is going to, a model for a black hole that isn't going to have infinite density in it, it's going to have to involve quantum mechanics, and we can't get it to work. Uh, the gravity around a black hole is just too strong, and at which point we absolutely have to use them both together, and they don't cooperate. And so until we can get a model that does, we're kind of out of luck. We kind of have to just take some guesses. And there are some guesses for what actually happens inside of an event horizon based on quantum mechanics. Some of it is that the event horizon is just kind of the bottom, right? There is no inside. That all the matter just kind of drifts toward the event horizon and then stops. That's the smallest it can ever be. It's considered what the firewall model, where basically like there's just this sphere of super high energy particles that will basically just vaporize and like particleize you, turns you into plasma. It's not fire, but it's sort of just a plasma sphere that can't get any smaller. And so that's one possibility. Another possibility is that when you get down to like the Planck scale, that there is an amount of space that a single point takes up, and so again, while it might have a very high density, it's not infinite. And so there are some suggestions, but we don't have any way to test it. It doesn't make any testable predictions, and so we can't know for sure which one is real and which one isn't. Lots of questions today. A black hole is like a divided by zero error in the universe. At the moment, kind of, but it's not like the universe divided by zero. It's not like there's this undefined location. It's just a zero or an infinity in the math, in the model. It's not in the universe. And so at the moment, black holes kind of look like a divided by zero error, but again, like I said, I suspect that we'll find that it isn't actually one. I think the universe is a lot more stable than our models give it credit for. Let's see. I have not seen a lady yet. I want to though. It looks very cool, but I have not seen it yet. I'm more of a I don't usually go to the movie theater anymore. I haven't done that in a while. And so I tend to be the person that waits for it to come out on DVD or something, and I'll rent it. So and watch it at home. So it probably won't be until then. I probably won't see it until then. But I want to see it. It looks amazing. Very well done. Let's see. Are the live videos more uncomfortable than teaching? Yes. Even with teaching, right? I can go in, I can prepare, and I have a lesson prepared, and I can kind of anticipate what questions students are going to ask. When I do these live streams, I have no idea what you're going to ask. We start with the $10 questions, which kind of sort of sets up the first half hour or so, but it's not. After that, you can basically ask any questions you want, and then I have to deal with it about anything. And so yes, it's more stressful. But just because something is stressful doesn't mean that I shouldn't do it, and it doesn't mean that it doesn't, you know, it's not something that everyone can enjoy, right? Sometimes stress is just a necessary part of life. Um, and it was less than 100 people online asking questions simultaneously. Yes, I think if I did a public live stream, it would just be insane, and I would barely see anyone's questions in the chat long enough to actually read them, let alone answer them. So I don't know that I would do a live stream Q&A. If I had some kind of event to do, like if I wanted to do something specific, I could probably do a live stream, but I couldn't take anybody's questions. It would just be too overwhelming for me. Let's see. When you try to explain to people that don't work in two sectors, the goal is to explain the idea and the concept. Yeah, so sort of going back to commenters being upset that I wasn't detailed enough. Sure. It gets, I mean, I get that. It's not just limited to the energy flow video. It happens occasionally, and it's just something that happens on educational videos. I know Henry Reich has talked about it before, where some people are upset with how he simplified it, and other people aren't. And so it's just a matter of taste, I think. Different people expect different things out of an educational video, and so there's no sense in getting angry. It doesn't make me wrong. It just makes me not for that person. Let's see. How was Awkward M's reaction to the Q&A? She's actually been reading the comments and enjoying them a lot. So that's kind of cool. The comments have been very, very positive, but I'm actually surprised by how many people have watched it. But she's really happy with how the Q&A turned out, and so am I. So I think it turned out to be exactly what she wanted. I mean, it was her idea to begin with. So we were watching, I think, Hank and Catherine Green do it like a quick one, and she was like, "Hey, I want to do that." And so I put the feelers out for questions, and there it was. So let's see. Should finish up here real quick. There will be a day when you can gather 10 to 20 people in a room for a live talk and stream it that way in public. Yeah, I mean that would be cool. I'd probably have to be much bigger than this in order to do that, to actually get people in one place. And then I could stream the chat to everybody else, which could work. Maybe there's a way for me to do a public Q&A, but then have like only supporters ask questions. I don't know. I'd have to figure out what kind of options are available. But all right, so I'll take one more question here. Have you seen Avengers Infinity War? I have not. I knew that it ended in a cliffhanger, and I was waiting for the cliffhanger to finish before I watched it. So I can watch the two movies. What was it? Infinity War and Endgame, I think, is the fourth movie. But so I can watch them both together and and not have to deal with a cliffhanger for 2 years. So um, I chose not to watch it, but I will. I will watch it eventually. My wife has a bit of an obsession with superhero movies, so we will definitely be watching it eventually. You can always perform experiments with streaming. I could definitely do that. I sort of run the ideas in my head a little bit, but that would take a lot of planning, and so maybe at some point in the future that would be fun, but definitely not right now. Okay, so on that note, I think it's 3:10, so we should probably finish up at this point. And so on that note, thank you all for showing up. This was a very active chat today. Really appreciated that. I almost couldn't keep up with the questions, but I think you did okay. And anyway, so thanks for showing up. It's been great as usual, and I will see you next month. Have a great rest of your day, rest of your night, whatever time zone you happen to be in. And I'll see you later.